Hello, dear students. Welcome to the Quantum Guru. Let's see this question number 3.19 of Irodov. The question states, a very long uniformly charged thread oriented along the axis of a circle of radius r rests on its center. With one of the ends, the charge of the thread per unit length is equal to lambda. Find the flux of the vector E across the circle area. So let's have the diagram of the problem. So here is the diagram. This is a circle of radius r, and along the axis there is a semi-infinite wire of linear charge density lambda is placed. One end is at the center. So we have to find the flux of electric field crossing through the area of the string. So for that thing, I will have to break this ring into a little ring, and one of the little ring is a ring of radius small r and thickness is dr. And let's see the electric field because of this semi-infinite wire at any point. So if I take say maybe I see this point somewhere here, or I can see at this point only. So because of this semi-infinite wire, there will be two components of electric field. One component will be perpendicular to the wire, like this. Suppose this is a wire. So at this point, there will be one component like that, and one component will be like that. So one component perpendicular to the wire has a magnitude k lambda by r, and one component parallel to the wire and away from the wire has the also same magnitude k lambda by r, and that will be true for all points. So at this is one of the point at a distance r here. So here electric field vector I am showing. This is one component E, and there will be another component E. So now I intend to find electric flux through this area. And we know that through some area, the flux is T phi is equal to E dot ds. Area is a vector whose direction is perpendicular to the plane of that element. This is a flat element, so at all points the normal is the same direction. So at this direction the normal is along. If I look from downwards, so normal depends on from where I look. Suppose I look from the downward, so to me the area vector will look towards me, towards the observer. So here the area vector will be like that, and that will be same at all these points. Area vector will be at all these points downward, dm. So there I have written ds, so let me write this ds also. So what is the overall area of this little ring whose radius is r and thickness is dr, and that area is nothing but 2 pi r dr. And flux, because of the overall electric field, because of this electrical flux is going to be zero, because this E is perpendicular to ds, and more directly speaking, flux is because of the field lines crossing through the surface. This E vector is not crossing through the surface, so because of this E there is no flux, and because of this E the flux is E into ds, because this E is parallel to ds. So I will simply write this is equal to E ds. And what is ds? Ds I have just told, ds is 2 pi r dr. And what is the value of E? E at a distance small r is k lambda by small r. So E is k lambda by small r. Putting the value of E here, k lambda by r, and this is 2 pi r dr. R and R gets cancelled. So overall flux would be k lambda 2 pi integration of dr from where to where, from 0 to capital R, such that the whole area of the ring is covered. And this integration will be simply capital R. And let me write k is equal to 1 upon 4 pi epsilon naught. There is a lambda, there is a 2 pi, and this is a capital R. So this is 2. So now the flux is lambda r divided by 2 epsilon. That is my answer. Thank you.